Hello, welcome to this video. This is 4-1 and we're going to talk about graphing square root equations. So let's go ahead and look at our learning target for today. We're going to learn how to graph radical functions by successfully identifying parameters of a function. This is something that you should be familiar with how to do. Identify A, B, H, and K, and as well as interpret the parameters to determine the transformations it occurs. So if you have an A value, that's going to obviously give a vertical dilation, a B value, a horizontal dilation, and H and K will be translations. And then additionally, we're going to start off with square root functions, so you'll have to know the key points that those bring. Let's go ahead and revisit some of our transformations that we have. We have parameters of A, and remember your A value is a multiplier to your outside values, and this is going to control vertical stretching and compressing. And if A is bigger than 1, you're obviously going to get that stretch. If it's between 0 and 1, you're going to get a compression. And if A is negative, then that's going to result in a reflection. Now, your B value or your 1 over B value, however you want to represent it, remember that this is really the opposite. Like what you see, the opposite effect happens, and it's paired with an X value, which should make sense. This is going to be underneath your radical symbol. So if your B value is bigger than 1, so if you take this, if you see a 1/2, then your B value is 2, and you have a horizontal stretch by a factor of 2. If you see a 2, a 3, a 4, a 5, and you're thinking, hey, there should be stretch there, well, remember you have to take the reciprocal value of this, okay? So that would actually be a horizontal compression. All your X values are going to get tighter together. And then obviously if your B value is less than 0, that's going to result in a horizontal reflection. Okay, don't forget H and K. Obviously where your H value, this controls moving left and right. And again, you're supposed to see the opposite effect. So if I have X plus 3, I'm not going right 3, I'm actually going left 3. It's always the opposite value. And then K, no tricks with K. K will just carry us up or down. Okay, just translations up or down. All right, so let's go ahead. In order to learn how to graph square roots, we have to know what a regular square root function looks like because we're going to graph the transformations. So let's investigate the parent function, f of x equals the square root of x. And f of x equals the square root of x, since it is a radical function, a square root function, I cannot have negative values be inside of the radicand. Thus, we have a restricted domain. So our domain is the x value is greater than or equal to 0. I don't want imaginary values. So our first x value that we're going to plug into our function is 0. And if I take the square root of 0, I get 0. So I get that point there. Next, I'm going to plug in 1. Makes sense. I plug in 1 and I get an output of 1. And I'm not going to plug in 2 next because I'm taking square roots. And I don't know off the top of my head, you know, exactly what the square root of 2 is with accuracy, but I do know, how about 4? What if I can plug in the square root of 4? That's going to give me a nice clean point of 2. And I'll also be purposeful by picking 9, which results in 3. So you can see here, here's our key points, and we graph a curve. You start at your end point, and you graph outwards. This is an increasing concave down function. So the range, if you're starting at 0, it's going to be increasing here for the parent function. And again, this could be decreasing based upon our parameters if we multiply by negative. End behavior. There's only one end behavior. And please do me a favor. This needs to be adjusted. I'm going to scratch out this notation. I'm going to give you the limit notation. So the limit of this function, we'll call it f of x. As our x values increase unbounded, x going to positive infinity, the y values are going to increase unbounded towards positive infinity. So we only have one end behavior on the right hand side. Okay, so there's a couple of procedures that we can use in order to graph square root functions using transformations, and I tend to use the first one. I will translate the function, the endpoint 0, 0 to h comma k. I just take it and I make it h comma k, and then this will have all of our translations built into every single point. Thus, I'll just stretch and compress or reflect all of the other points. Stretch, compress, and or reflect all the other points. And I just graph them using my endpoint or my anchor point, as I call it, to build in those transformations, okay? You can use the other option where you stretch and compress all the other points and then translate them, but I think that's a little bit tedious. And I'll show you what I mean here in example 1. So here is example number 1. And we're asked to go ahead and graph the function using transformations, describe the domain and range using set and interval notation, and describe the end behavior. So the first thing that I'm going to do is I'm going to identify the transformations. I have an a value that's -2, we have an h value that's -3, and we have a k value that is -4. So based upon this, here's your second success criteria, right? This is the first one. Your second one, I would expect you to be able to look at this and say, hey, I'm going to stretch vertically and I'm going to reflect. I'm going to be moving to the left and I'm going to be moving down. So hopefully you can do that. The second thing that we need to do is we need to go ahead and we need to take our end point or the anchor point, and we're going to move it from 0, 0 to h comma k, to h comma k. So -3, -4. There's your h and your k. So I'm going to go ahead and plot this point, and I'll put it in red. -3, -4. There we go. So there is our end point. And what I'm going to do next now is I'm going to use that point. I'm going to treat that kind of like a pseudo origin, almost like a 0, 0, and I'm going to plot all the other points from that. So I'm going to go back to my key points, and my key points, x comma y, in case you forgot, 0, 0, 1, 1, 4, 2, and 9, 3. I'm now going to go ahead and I'm going to take these points and I'm going to add the stretch, compression, reflection components, which in this case is going to be only the a value. And that's going to affect my y values. I'm going to put here a times y. So my x values are untouched, 0, 1, 4, 9. Nothing happens to them. I just have to multiply my x values, the 0, the 1, the 2, and the 3, times my a value, which is a factor of -2. So -2 times 0, -2 times 1, -2 times 2, -2 times 3, and these are going to be the new y values that we're going to use. So we get 0. Again, your anchor points, nothing's going to happen to your end point, anchor point. -2 times 1, -2. -2 times 2, -4. -2 times 3, -6. Okay, so I can go ahead and I can plot all of these. So I'm going to start here, 0, 0. There's the first point. That's my anchor point. And then 1, -2. So I'm going to go right 1 and then down 2. Oh, I see what I did. Whoop. This is a +4. My k value is not a -4. It's a +4. I was like, this doesn't look familiar. So let me just go back up here. -3, +4, I'm up here. Okay. Sorry about that. So 0, 0, and then I'm going to go 1, -2. So I'm going to go right 1, and then I'm going to go down 2. So right 1, down 2. So there's point 2. Then you go back to your anchor point to plot the next point. So then 4, -4. So right 1, 2, 3, 4, down 4. 1, 2, 3, 4, and you'll have a 0 there. Then 9, -6. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then down 6. 1, 2, 3. One too many. Okay. So our curve then for this function, you're going to start at your endpoint and you just curve out. through these points. Another kind of feature is that you should have equal width between your points vertically for your y values. So I should have a space here that's consistent. So down 2, and then from here, down 2. Okay, so there's our function. Here is the transformed function g of x, and our domain. The domain is all of the x values. We start here at -3, and I want x values that are bigger than -3. So x is greater than or equal to -3, and as an interval notation, that would be -3, comma, infinity. The range, my y values, notice 4 is the maximum. So my y value must be actually less than or equal to 4. And I'm including that endpoint because I have a point there. And so that's going to be -infinity to 4. Notice I always use parentheses on the infinities. I'm using brackets here on the endpoints because I'm including that point. And I always put them in order. So it's -infinity to 4. All my y values are from -infinity to 4. If you put 4, comma, -infinity, that's wrong. It must be lower value first and then upper value for interval notation. End behavior, please write a limit notation. So this is the limit of g of x as x goes to, and we're just looking at the end where it's curved. So notice it's right side going down. So the limit as x is going to positive infinity, and we're going to negative infinity. Okay, so there is example 1. And again, looking back at the success criteria, hopefully you were able to identify your parameters, unlike me. Don't switch the k value. And then you could identify like the types of effects that were going to happen, and then you could graph that square root function. Okay, I want you to go ahead and pause me. I've been talking a lot. I want you to try example number 2, which is here, and then I'll come on here and you can check your work. All right, pause me, try this example. All right, hopefully you were able to identify your parameters, A3, H5, K, -1. You're going to go right 5 and then down 1. So here is your anchor point or your end point. Remember, it's just H, comma, K. And then your other points come from taking your key points. Remember your key points, X, comma, Y, 0, 0, 1, 1, 4, 2, 9, 3. And you're just multiplying these Y values times A. So 1 times 3. 2 times 3, 3 times 3, and we did have one point go off the graph. Your domain here is going to be all x values that are greater than or equal to 5, and then as an interval notation, this is 5 to infinity. The range is y values greater than or equal to -1, and as an interval notation, it would be -1 to positive infinity. Your end behavior, it's the limit as x goes to positive infinity of g of x is equal to positive infinity. Our right side is going up. Okay, how'd you do? Good? Awesome, piece of cake. Let's go ahead now and look, another practice one. Okay, go ahead, try this one. This one's just slightly different. I'll post the solutions here in a second. All right, here's the solution. A value -1/2, H is 0, K is 4. So your anchor point, you just get shifted up 4. Your A value will compress all of your Y values by 1/2, and you have a negative. So you're going to see some reflection. Really, really tight, skinny, almost flat line. It should have a concavity, concave up. And then here's the domain and the range. Take note, double check your range. It should be -infinity up to 4. 4 is the maximum. And then your end behavior, the right side's going down. You're decreasing. So limit as x approaches infinity of g of x is -infinity. Okay, let's go ahead and look at an example now where we have a b value. So I don't have an a value, but I do have this b parameter here. I see a -2. So I know that my b value is the reciprocal of this, which is -1/2. So you always flip that. Our h value, also the opposite. Remember, anything that affects the x really is the opposite. And then our k value is -5. Okay, so I'm going to go ahead and I'm going to take my anchor point, -4, -5, and we'll plot this. So -4, -5. which is right here. And then I'm going to take my key points and I'm going to multiply times my b parameter. So the b value affects my x's. Okay, so it's bx and then my y's. So here the y values are unaffected. So 0, 1, 2, and 3, those are unaffected. But my 0, my 1, my 4, and my 9, all of these are going to get multiplied times this b factor, which is a negative 1/2. So nothing happens to 0. Negative 1/2 of 1 is negative 1/2. Negative 1/2 of 4 gives me negative 2. And negative 1/2 of 9 is negative 4.5. Okay, so instead of going right, I'm going to go left. So I'm going to go left 1/2, up 1. I'm going to go left 2, 1, 2, and then up 2. And then back to my anchor, and I'm going to go left 4.5, 1, 2, 3, 4.5, and then up 3. Okay, and there is our curve. Not too bad. Remember that negative on the inside there, that's going to be horizontal reflection, and your reciprocal does the opposite, so that's compression. Okay, domain, this is a change to domain. I reflected my x values, so domain gets changed. So now being greater than, x being greater than or equal to a certain value, it's x is less than or equal to negative 4, and that's negative infinity to negative 4 in interval notation. The range, all my y values are greater than or equal to negative 5, which is the minimum value. So negative 5 to positive infinity. And then my end behavior, notice I'm switching directions. So the limit of g of x, now my x values are decreasing without bound towards negative infinity. So the left side, and we're going up. So that's a positive infinity. Not too shabby. Okay. Whew. Next example, we have a 3/4. Woo! Okay. So again, I'm going to take the reciprocal here. We have 4/3. 4/3. Our h value is a positive 1, and our k value is a negative 2. So anchor point, 1, negative 2. So right 1 up 2. There's our anchor point. And then I'm going to go ahead and I'm going to make my little table. So bx times y. Again, the y values 0, 1, 2, 3 are unaffected. And we have 0 times 4/3. That's 0. 1 times 4/3. That's 4/3. We have 4 times 4/3. That's 16/3. And we have 9 times 4/3. So 9 times 4/3, the 3 is going to cancel, and we should get 12. Okay. Yeah, because we're stretching. All right. So 16/3. I don't know what that is. That's off the top of my head. It's about what, 5 and 1/3. Okay, so we'll roll with that. Let's go ahead and plot these. Okay, so 4/3 and then 1. So right 1, 2, sorry, 4/3. So 1 1/3, and then we're up 1. Okay, and then the next point was that 16/3. So 5 1/3. So I'm going to go right 1, 2, 3, 4, 5 1/3, and then we'll go up 2. Okay, and then write 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're off the grid by 1, and we're going to go up 3. Okay, and we're going to go ahead and then just draw our smooth curve. through these points. Okay. Domain. These are the x values greater than or equal to 1, and that's 1 to infinity. Range, y value is greater than or equal to 2, so that's 2, infinity. And end behavior, the limit of g of x as x goes to positive infinity is positive infinity. Okay, we got a couple of practice problems here. I'd like you to go ahead, try this next one, and then I'll post the solutions. All right, hopefully you have these key points, 0, 0. You should have then had -2, 1, -8, 2, and -18. That one will carry you off the grid to get to 3. But our parameter of the b value of being -2 stretches us by a factor of 2, and we get the negative, which reflects us to the left. Your domain and range, x is less than or equal to 2, so -infinity to 2, and your range y is greater than or equal to 3, so 3 to infinity. The end behavior, the limit of g of x as x goes to -infinity, because we're going to the left, that's going to go to positive infinity. Here's the last practice problem. Please pause me and try this example. All right, and here is the last solution to this practice problem. Your anchor point is at -3, 1. Your domain x is greater than or equal to -3, y is greater than or equal to 1, and your limit of g of x as x goes to positive infinity is positive infinity. Again, here's your key points. You have a b value which multiplies your x values to get that horizontal stretch. Okay, so just recapping, hopefully in this video you learned how to graph some radical functions and specifically the key points of a square root function with transformations. Catch you in the next video. Comment, subscribe, thumbs up, all of it at RadMathDad. See you guys later.